Hello everyone. In this video, I am going to make a audio recording on the chapter ethers and epoxides. Introduction. Organic compounds having COC as the functional group are called the ethers. This general formula is ROR dash, where R and R dash may be the same or different alkyl or aryl groups, or one of them may be an alkyl and then other aryl group. The divalent oxygen is also called the ethereal oxygen. Ethers in which the groups R and R dash are the same are called simple or symmetrical ethers, while those in which the groups R and R dash are different are called mixed or unsymmetrical ethers. For example, diethyl ether symmetrical, diphenyl ether symmetrical, ethyl methyl ether unsymmetrical, methyl phenyl ether unsymmetrical. Ethers may be regarded as the functional isomers of alcohol. For example, both dimethyl ethers and ethyl alcohol have the same molecular formula C2H6O but different functional groups. Classifications. Ether may be broadly classified into the following three categories. Aliphatic ethers, in which R and R dash may be saturated or unsaturated groups derived from aliphatic hydrocarbons, for example, ethyl methyl ether, methyl vinyl ether, divinyl ether. Aromatic ethers, in which either one or both R and R dash are aryl groups, for example, methyl phenyl ether, ethyl phenyl ether, diphenyl ethers. Aromatic ethers are further subdivided into phenolic ethers and diaryl ethers. Ethers in which one of the groups is aryl while the others is alkyl are called phenolic ethers or alkyl allyl ethers. On the other hand, ethers in which both the groups are aryl are called diaryl ethers. For example, methylphenyl ether, diphenyl ether. Now, cyclic ethers. Ethers in which the oxygen is present in a ring are called cyclic ethers. They are further classified as simple cyclic ethers or crown ethers. Simple cyclic ethers. Cyclic ethers containing 1, 2 or 3 oxygen atoms in the rings are called simple cyclic ethers. For example, oxyrane, oxetane, tetrahydrofuran, tetrahydropyran, 1,4-dioxane, 1,3,5-trioxane. Crown ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because the three-dimensional shape resemble the shape of a crown. They are usually named as X crown Y, where X is the total number of atoms in the ring and Y is the total number of oxygen atoms. For example, 12 crown 4, 15 crown 5, 18 crown 6. Nomenclature. Open chain or acyclic ethers. Common system. The common names of ethers are derived by naming the two alkyl or aryl groups linked to the oxygen atom in alphabetically order and adding the word ether. In case of symmetrical ethers, the prefix di is used before the name of the alkyl or the aryl group. Some aromatic ethers, however, have their special names. For example, methyl phenyl ether is called anisole and ethyl phenyl ether is called phenantol. IUPAC name. In the IUPAC system, ethers are named as alkenes. The ethereal oxygen is taken with the smaller alkyl group and forms a part of the alkoxy group, while the larger alkyl group is considered to be a part of alkane. The common IUPAC name of some ethers are given here, like dimethyl ether and its IUPAC name is methoxymethane. Ethyl methyl ether, its IUPAC name is methoxyethane. Diethyl ether or ethyl ether, its IUPAC name is ethoxyethane. Now, isopropyl methyl ether, its IUPAC name is 2-methoxypropane. Diisopropyl ether, its IUPAC name is 2-propoxy-2-propane. Methylphenyl ether or anisole, its IUPAC name is methoxybenzene. Ethylphenyl ether or phenantol, its IUPAC name is ethoxybenzene. Diphenyl ether, its IUPAC name is phenoxybenzene. For further illustrations, the IUPAC name of some other acyclic ethers are given below. 2-methoxyethanol, 2-chloroethoxyethane, bromoethoxybenzene, 2-methoxy-2-methylpropane, 3-methyl-1-butoxybenzene. Acyclic polyethers. Long-chain polyethers are named as oxo-derivatives of the alkane corresponding to the total number of carbon and oxygen atoms present in the chain. For example, 2,5-dioxohexane, 2,5-trioxanone. Cyclic ethers. Common name. In the common system, the three-member cyclic ethers are named as oxides of the alkyline from which they are derived. For example, ethylene oxide or epoxide, propylene oxide, isobutylene oxides. The name of some cyclic ethers are based upon the names of the fully hydrogenated products. For example, furan, tetrahydrofuran, 4H-pyran, 2H-pyran, tetrahydropyran. IUPAC names. The IUPAC names of cyclic ethers when n is equal to 2, 3, 4, 5, 6 are given below. Oxirane, oxetane, oxolane, oxane, oxapane. The italicized portion of these names are the suffix used to represent the size of saturated heterocycle ring then with n atoms. In case of substituted cyclic ethers, the substituents are indicated by numerical prefixes with the oxygen atom getting number 1. Now trans 2,3-dimethyl-oxirane or trans dimethyl-oxirane, 3,3-dichloro-2-methoxy oxetane, cis 2-chloro-6-ethyl-oxypane. Oxa names. Cyclic ethers are also named as oxa derivative of their corresponding cycloalkanes. Oxacyclopropane, oxacyclobutane, oxacyclopentane, oxacyclohexane, 1,4-dioxacyclohexane. Methods of formations. Ether can be prepared by the following general methods. First, from alkyl halides, Williamson synthesis. This is one of the best methods for the preparation of ethers. It involves the treatment of an alkyl halide with a suitable sodium alkoxide. The sodium alkoxide needed for the treatment of an alkyl halide with a suitable sodium alkoxide. The sodium alkoxide needed for the purpose is prepared by the action of sodium on suitable alcohol. The reaction in fact involves the nucleophilic displacement of the halide in form of the alkyl halide by the alkoxide ion by SN2 mechanism. This method can be used for preparation of both the symmetrical and unsymmetrical ether. For example, sodium ethoxide plus ethyl bromide gives diethyl ether under the condition 333 Kelvin temperature. For sodium tertiary butoxide plus methyl bromide gives tertiary butyl methyl ether or NABR on heating. Similarly, alkyl aryl ethers can be easily prepared by treating sodium phenoxide with alkyl halides. For example, sodium phenoxide plus methyl bromide gives anisole plus sodium bromide on heating. Like halides, ions sulfate ion is a good leaving group. Therefore, in Williamson synthesis, alkyl halides may be replaced by alkyl sulfates. For example, sodium ethoxide plus dimethyl sulfate gives ethyl methyl ether or sodium sulfate. Sodium phenoxide plus diethyl sulfate gives phenetol plus sodium sulfate. Now, limitations. A proper choice of alkyl halide and sodium alkoxide to be used in Williams synthesis is necessary in view of the following consideration. Since a halogen attached to a double bond or an aromatic ring cannot be readily displaced by a nucleophilic reagent, therefore, aryl halides are not generally used in Williamson synthesis. Therefore, for the synthesis of simple alkyl aryl ethers, the reaction is carried out between an alkyl halide and sodium phenoxide and not between aryl halide and sodium alkoxide. For example, sodium phenoxide plus ethyl iodide gives phenetol or sodium iodide on heating. Bromobenzene plus sodium ethoxide on heating gives no reaction. However, if the halogen is activated by the presence of electron withdrawing group at ortho and para positions with respect to the halogen atom, such activated aryl halides can be used in Williamson synthesis. For example, para-nitrobromobenzene plus sodium methoxides give para-nitroanisole or sodium bromide. We have stated above that Williamson synthesis involves nucleophilic attack of the alkoxide phenoxide ion on an alkyl halide. Now, depending upon the structure, alkyl halide may undergo substitutions or elimination reactions. Therefore, for the success of this reaction, it is essential that the alkyl halide used must be such which predominantly undergoes nucleophilic substitution, since primary alkyl halides are more susceptible to SN2 reactions. Therefore, best yields of unsymmetrical ethers are obtained when the alkyl halides are primary and alkoxides may be primary, secondary, or tertiary. For example, tertiary butyl ethyl ether is prepared by treating ethyl bromide with the sodium tertiary butoxide. Sodium tertiary butoxides plus ethyl bromides gives tertiary butyl ethyl ethers on heating. The above ethers cannot be prepared by treating sodium ethoxide with tertiary butyl chloride or bromide, since under these conditions an alkene, that is isobutylene, is the main product with secondary alkyl halides. Both substitution and elimination occurs together, giving a mixture of ethers and alkenes, but with tertiary alkyl halides only elimination occurs, giving alkenes. Thus, when a mixture of tertiary butyl bromide is treated with the sodium ethoxide, tertiary butyl ethyl ether is not formed, but instead 2-methylpropene is formed due to elimination reaction. Tertiary butyl bromide gives 2-methylpropylene on elimination. Due to steric hindrance, secondary alkyl halides are also prefers to undergo elimination rather than substitution. For example, bromopropane on reaction with the sodium ethoxides gives propene or 2-ethoxypropane. Reaction of alkyl halides with dry silver oxides ether can also be prepared by heating an alkyl halide with the dry silver oxide. For example, ethyl bromide plus silver oxides gives diethyl ether plus sodium silver bromide. From alcohol, ether may be prepared from alcohol as follows: by dehydration of alcohol. Ether may be prepared by dehydration of alcohol either in the presence of acid or heated alumina. Acid catalyzed dehydration. Symmetrical ethers can be prepared by dehydration of alcohol with concentrated H2SO4 at 413 Kelvin. The yields of ether, however, depends upon the nature of the alcohol, whether primary, secondary, or tertiary. Since in these reactions 2 molecules of an alcohol lose 1 molecule of water, therefore it is better called as intermolecular dehydration. Limitation: though this method is useful for the large scale production of ethers, it has two major drawbacks. The preparation of ethers is always accompanied by the formation of alkene due to intramolecular dehydration of alcohol. However, in case of primary alcohols, the alkenes are formed only to small extent, which can be further suppressed by using a large excess of the alcohol. In case of secondary alcohol, alkenes are formed in much larger amounts than ether, but in case of 3-degree alcohol, exclusive formation of ethers occurs. Thus, the order of dehydration of alcohols leading to the formation of ethers follows the sequence: primary, then secondary, and then tertiary. Therefore, dehydration of alcohol is used only for preparing ether from primary alcohols. This method is not suitable for unsymmetrical ethers because the complex mixture of ether always obtained. For example, ROH plus HOR dash on concentrated H2SO4 gives ROR plus ROR dash plus R dash OR dash plus VH2. Mechanism: this reaction is an example of a nucleophilic substitution reaction in which protonated alcohol molecule act as a substrate, water as the leaving group, and another molecule of alcohol as a nucleophile. The reaction may follow either first order kinetics or the second order kinetics depending upon the nature of the alcohol used. In general, 1-degree alcohol follow SN2 mechanism, while 2-degree alcohol first followed SN1 mechanism. In SN2 mechanism, we go through a transition state, but in SN1 mechanism, we go with the carbocation. Catalytic dehydration. Dehydration of alcohol to ethers can also be achieved by passing the vapors of an alcohol over heated alumina at 523 Kelvin. For example, ethyl alcohols on aluminium oxide and 523 Kelvin temperatures give diethyl ether. By the action of diazomethane on alcohols or phenols, methyl ethers can also be prepared in excellent yields by the action of diazomethane on alcohols or phenols in presence of tetrafluoroboric acid as catalyst. From alkenes, ether can be prepared from reactive alkenes by the following two methods. First, direct addition of alcohols in presence of acids as catalyst. For example, 2-methylpropene plus methanols gives 2-methoxy 2-methylpropene on reaction with a sulfuric acid, and these reactions occur with the Markovnikov addition rule. The main disadvantage of this method is that sometimes the initial formed carbocations rearranges to the more stable carbocation, which then react with alcohol to form rearranged ethers. For example, 3,3-dimethyl 1-butene on reaction with the sulfuric acid and ethanol gives 2-ethoxy 2,3-dimethylbutane, which is a rearranged product, and 2-ethoxy 2,2-dimethylbutane, which is a normal product. Indirect addition of alcohols, alkoxymercuration reduction. Alkanes readily react with the mercuric trifluoroacetate in the presence of an alcohol to give alkoxymercurial compound, which upon reduction with NaBHO4 in acidic mediums gives ethers in high yields. For example, propene plus alcohol reaction with the mercuric trifluoroacetate gives on further reaction with NaBHO4 gives 2-ethoxypropane. This two-step product is called alkoxymercuration reduction or alkoxymercuration demercuration and gives ether in accordance with the Markovnikov addition of alcohols to alkenes. The main disadvantage of this method of Williamson synthesis are the reaction does not involve carbocation intermediate, hence there are no rearrangement in this reaction. 3,3-dimethyl 1-butene plus ethanol gives 2-ethoxy 2,2-dimethylbutane. Absence of complete elimination reaction from Grignard reagents. Higher ethers can be prepared by treating alpha halo ethers with the suitable Grignard reagents. For example, methoxychloromethane gives ethyl methyl ether plus chloromagnetic iodine on reaction with the dry ether. Physical properties, physical state, color and odor. Dimethyl ether and ethyl methyl ethers are gases at ordinary temperatures, while the other lower homologues of ethers are colorless liquid with the characteristic ether smell. Dipolar nature. Because of the greater electronegativity of oxygen and carbon, the carbon-oxygen bonds are slightly polar and thus have a dipole moment. Since the two carbon-oxygen bonds in ethers are inclined to each other at an angle of 110 degrees, the two dipoles do not cancel each other. As a result, ethers have a dipole moment. For example, the dipole moment of dimethyl ether is 1.3 d and that of diethyl ether is 1.18 d. Boiling points. Ether are isomeric with the monohydric alcohols, but the boiling point are much lower than the isomeric alcohols. This is due to the reasons that unlike alcohols, ethers do not form hydrogen bonds. As a result, ethers do not show molecular association and hence have lower boiling points than the corresponding alcohol. Further, the weak polarity of the carbon-oxygen bonds does not appreciably affect the boiling points of ethers, which are about the same as those of alkanes with comparable molecular masses. Solubility. Ethers containing up to 3 carbon atoms are soluble in water. The solubility of other lower ethers in water is comparable to those of the corresponding alcohol. For example, like ethanol, dimethyl ether is completely miscible with the water. Similarly, both diethyl ether and N-butyl alcohol are soluble in water to the same extent, that is 8 gram per 100 gram of water. The solubility of lower ethers in water is due to the formation of hydrogen bond between water and ether molecule. As the molecular mass increases, the solubility of ethers in water decreases due to a corresponding increase in the hydrocarbon portion of the molecules. Ethers are, however, fairly soluble in common organic solvents such as alcohol, benzene, chloroform, acetone, etc. Density. All ethers are lighter than water. Chemical properties. Ethers are relatively inert compounds, almost as inert as alkanes. Under ordinary conditions, they are stable to bases, dilute acids, catalytic hydrogenation, and to most other reducing agents. This is due to the reason that the functional group of ethers or does not contain any active sites in their molecule as compared to hydroxyl group of alcohol and phenols, even though the oxygen atom in both these functional groups containing two lone pair of electrons. However, under specific conditions ethers undergo the following reaction. Reactions of the ethereal oxygen on account of the presence of two lone pairs of electrons on the oxygen atoms. Ether behave as a Lewis basis and thus undergoes reaction involving the formation of coordinate bond as discussed below. Action of concentrated acids, formation of oxonium salts. The oxygen atom in ethers has two lone pair of electrons. As a result, ether behave as a Lewis basis and thus dissolves in cold concentrated inorganic acids to form stable oxonium salts. For example, ether on reaction with the hydrochloric acids give dialkonium chloride, dialkyl oxonium chloride. Formation of coordination complexes. Being Lewis bases, ether form coordination complexes known as ethereals with Lewis acids such as BF3, AlCl3, FeCl3, Grignard reagents, etc. Diethyl ethers on reaction with the BF3 gives boron in fluoride etherate. Diethyl ether on reaction with the Grignard reagents give Grignard reagent etherate. Due to the formation of these complexes, Grignard reagents dissolved in ethers. That is why Grignard reagents are usually prepared in ethers. They, however, cannot be prepared in benzene because benzene has no lone pair of electrons and hence cannot form complexes with them. Reaction involving the cleavage of carbon-oxygen bond with halogen acid. Ether are readily cleaved by hydroiodic acids or hydrobromic acids at 373 Kelvin temperature, form an alcohol and an alkyl halide. For example, ethers gives alcohol and alkyl halides on reaction with hydrohalo acids at temperature 373 Kelvin. For example, diethyl on reaction with hydroiodic acids gives ethyl iodide and ethyl alcohol. However, if excess acid is used, the alcohol first formed react further with the halogen acids to form the corresponding alkyl halide. The overall reaction may be written as ROR plus 2HI gives 2RI plus H2O. On diethyl ethers, on reaction with hydroiodic acids at temperature 373.5 Kelvin gives ethyl iodide and water. Similarly, cyclic ethers are readily cleaved by hydrobromic or hydroiodic acids to yield dihaloalkanes. For example, tetrafluorohydrofuran gives 1,4-dibromobutane and water on reaction with the hydrobromic acids at 373 Kelvin. Reactivity of halogen acids. The order of reactivity of halogen acids follows the sequence hydroiodic acids, then hydrobromic, and then hydrochloride acid. As discussed above, the cleavage of ethers by halogen acids in fact involves the nucleophilic attack of the halide ion on the protonated ether molecule. Obviously, greater the nucleophilicity of the halide ion, more reactive is the halogen acid, since the nucleophilicity of the halide ion follows the sequence iodine, bromide, and chlorine. Therefore, the reactivity of the halogen acids follows the same sequence, that is hydroiodic acids, then hydrobromide, and then the hydrochloride. Mechanisms. The cleavage of ethers by halogen acids occur by the following mechanism. Step 1. Ether being Lewis basis undergoes protonation to form oxonium salts. Step 2. The protonated ethers thus formed undergo nucleophilic attack by the halide ion either by SN1 or SN2 mechanism depending upon the nature of the groups R and R dash and the reaction conditions to form a molecule of an alkyl halide with the displacement of the weak basic alcohol molecules. If the group R and R dash are primary, the reactions occur by SN2 mechanism, and if the secondary or the tertiary, the reactions occur by SN1 mechanism. Site of cleavage. The site of cleavage of unsymmetrical ethers by halogen acids depends upon the nature of the group R and R dash. The following cases arise. If both the group R and R dash are primary, the alkyl halides is always obtained from the smaller alkyl group. For example, ethyl methyl ether, methyl iodide plus ethyl alcohol. If one group is methyl and the other is a primary or a secondary alkyl group, the reaction occurs by SN2 mechanism. Due to steric hindrance, the halide ion is always attacks the smaller alkyl group, that is CH3 group, to gives methyl iodide, while the bulkier alkyl groups gives the alcohol. For example, methyl isopropyl ethyl plus concentrated hydroiodic acids gives methyl iodide and isopropyl alcohol. If one group is methyl and the other is a tertiary alkyl group, the reaction occurs by SN1 mechanism and the formation of product is controlled by the stability of the carbocation resulting from the cleavage of carbon-oxygen bond in the protonated ether. Since tertiary alkyl carbocation is much more stable than the methyl carbocations, therefore the alkyl halide is always derived from tertiary alkyl group and the alcohol from the smaller group, that is methyl group. For example, tertiary butyl methyl ether plus concentrated hydroiodic acids gives tertiary butyl iodide plus methyl alcohol. It may be emphasized here that the high polarity of the solvent present in concentrated hydroiodic acid has favored SN1 mechanism. However, if the cleavage of a tertiary butyl methyl ether is carried out with anhydrous HI is ether, the low polarity of the solvent would favor SN2 mechanism and hence I negative ion will attack the less hindered methyl group, giving methyl iodide and tertiary butyl alcohol. Tertiary butyl methyl ethers gives methyl iodine and tertiary butyl alcohol under the condition anhydrous hydroiodic acids ether SN2 mechanism. Cleavage of alkyl aryl and diaryl ethers. In case of alkyl aryl ethers, the product are always phenols and an alkyl halides and never an aryl halides had an alcohol. For example, methyl alcohol, iodobenzene do not gives do not do not come when any sol react with hydroiodic acid at 375 Kelvin, but phenol and methyl iodide came as a product when hydroiodic acid at 373 Kelvin. The carbon atoms of the phenyl group are sp2 hybridized while that of alkyl group are sp3 hybridized. sp2 hybridized carbon being more electronegatives repels the nucleophilic, while the sp2 hybridized carbon being less electronegative attacks the nucleophile. In other words, nucleophile attack by the halide ions occurs more easily on the alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, a phenyl group is much bigger in size than an alkyl group. Therefore, because of the steric hindrance of the bigger phenyl group, the halide ion attacks the alkyl group, leading to the formation of alkyl halide and phenol. It may, however, be noted that the phenol is not converted to iodobenzene even with excess of HI. Diaryl ethers are not cleaved by HI because both the carbon atoms to which the oxygen is attached are sp2 hybridized and hence repels the nucleophilic halide ions. Jessel method, cleavage of alkyl aryl ether by hydroiodic acid form the basic of Jessel method for the estimation of alkoxy group such as methoxy and ethoxy group. In such ethers, a known weight of the phenolic ether is treated with an excess of concentrated hydroiodic acids. The alkyl iodide product as a result of cleavage of ethers by HI is treated with an ethanolic solution of silver nitrate. The precipitate of silver iodide thus is formed, washed, dried and weighed. From the amount of silver iodide formed, the percentage of alkoxy group can be estimated. With sulfuric acid, on heating with dilute sulfuric acid under pressure, ether are hydrolyzed to alcohols. Ethers plus waters gives alcohols when react with the dilute H2SO4 under pressure. Diethyl ether plus waters gives ethyl alcohol under pressure and dilute sulfuric acids and heat. When heated with concentrated H2SO4, ether reacted in the same manner as with halogen acids to form an alcohol with an alkyl hydrogen sulfate. For example, diethyl plus concentrated sulfuric acid gives ethyl alcohol and ethyl hydrogen sulfate, that is tertiary butyl methyl ethers gives isobutylene plus methanol, reaction involving the alkyl group. Action of air and light, that is auto-oxidation, formation of peroxides. When exposed to air and light for a long time, ethers are oxidized to form hydroperoxides or simply peroxides. Diethyl ether plus oxygen gives 1-ethoxy-ethyl hydroperoxides. It is a free radical reaction and oxidation reaction occur at the carbon atom next to the ethereal oxygen to form hydrogen peroxides. These peroxides are very dangerous compounds since they decompose violently at high temperatures. Therefore, serious explosions may occur during distillation of all samples of ether if peroxides are not removed. Presence of peroxides in old samples of ethers may be detected by shaking them with a freshly prepared solution of FeSO4 followed by the addition of KCNS. Appearance of red color indicates that the presence of peroxides. A simple method is used to remove the peroxide is to shake and all samples of ether with either an aqueous solution of Ki or a ferrous salt. When ether peroxides are reduced to ethers, and I negative ion is oxidized to I2 or Fe2 positive salt or oxidized to Fe3 positive salt. Halogenations. Ethers react with a Cl2 or Br2 to give substitution products. The extent of halogenation, however, depends upon the reaction condition. For example, diethyl ethers react with the chlorine in the dark to give alpha alpha dash dichloro. Diethyl ethers, however, in the presence of light and excess of fluorine, all the hydrogen atoms are substituted to give perchlorodiethyl ethers. Diethyl ether plus excess of Cl2 gives perchlorodiethyl ether plus 10 hydrochloric acids. Now, epoxides. Three-member cyclic ethers are called epoxides. In the common system, they are called alkyl oxides, but in the imapaired system, they are called either alkene oxides or epoxy oxidation. For example, epoxy ethanes or ethene oxides, alkene oxides, epoxy alkanes or oxidanes. For example, epoxy ethanes or ethene oxides, ethylene oxides, H2,3-butane oxides or Z2,3-epoxy-butane. Synthesis of epoxides. There are two main laboratory methods for the synthesis of epoxides. They are perbenzoic acids, metachlorobenzoic acid, peroxydifluoroacetic acids in the inner solvents such as CH2Cl2, CHCl3 or CCl4 gives epoxides. Due to the formation of epoxides, the oxidations of alkenes with the para-acids is commonly known as epoxidation. For example, alkene plus peroxyacids gives epoxides and carboxylic acids. CH2 double bond CH2 plus peroxybenzoic acids gives ethylene epoxides or benzoic acids with the carbon tetrachlorides. 2-methylbutene plus peroxybenzoic acid gives 2,2 trimethyloxidane and carboxylic benzoic acids on reaction with CCl4. Mechanism. Peroxides act like electrophiles and the reaction is believed to proceed in the following mechanism. Ethylene plus peroxybenzoic acids with reaction with CCl4 gives ethylene epoxides and benzoic acid. From hydrohydrins. When halohydrins prepared by addition of hypohalous acids to alkenes are treated with a base, HS is eliminated and epoxide is formed. For example, ethylene plus Cl2H2O, ethylene chlorohydrin plus KOH gives ethylene epoxides plus KCl plus H2O. Cyclohexane plus Br2 plus H2O gives 2-bromocyclohexanol plus dilute NaOH gives 1,2-epoxy cyclohexanes plus sodium bromide plus water. Mechanism. It may be noted the synthesis of epoxides by base treatment of halohydrine is actually an intermolecular Williamson synthesis. Bromohydrine on reaction with NaOH plus H2O gives a transition state. When Br negative happens through this, epoxide is formed. Manufactures of ethylene oxides. It is manufactured by passing a mixture of ethylene and air under pressure of a silver catalyst at 573.5 Kelvin temperature. Ethylene plus oxygen gives ethylene oxides on reaction with silver and to 573 Kelvin temperature. Chemical reaction of epoxides as cyclic ethers and cyclic ethers containing 5 or 6 membered rings such as tetrahydrofuran and 1,4-dioxanes are quite inert and are often used as a solvent. 3-member cyclic ethers, that is Epoxides, on the other hand, are highly reactive. This is due to the reasons that three-membered rings are highly strained, that is, they have considerable angle strain. Because of their highly strained nature, epoxide rings can be opened by a variety of nucleophilic reagents under much milder conditions. Consequently, most of the reaction of epoxides are the ring opening reactions. This can be catalyzed both by acids and bases. For example, acid catalyzed ring cleavage of epoxides. Due to the large angle of strains, epoxides are readily hydrolyzed by dilute mineral acids at room temperature to form corresponding 1,2-diols. For example, ethylene epoxides plus water gives ethylene glycol. Similarly, halogen acids and alcohol in presence of acids can bring about the cleavage of epoxides. So ethylene oxides plus HBRs give 2-bromoethanol. Mechanism: in the acid catalyzed hydrolysis of epoxides, the oxygen atom of the epoxide rings first accepts a proton to form protonated epoxides. The protonated epoxides then undergo nucleophilic attack by water to give a trans 1,2-diol. Base catalyzed ring cleavage of epoxides. Unlike ordinary ethers, epoxides can also be cleaved under basic conditions: ethylene oxides plus ethylene glycol. नहीं Base catalyzed ring cleavage of epoxides. Unlike ordinary ethers, epoxides can also be cleaved under basic conditions. Ethylene oxide plus water gives ethylene alcohol. Similarly, sodium alkoxides, ammonia amines can also bring about cleavage of the epoxide rings. Sodium methoxides plus 2-methoxyethanol. Mechanism: due to the greater electronegativity of the oxygen than carbon, the carbon atom of the epoxide rings carries a small positive charge and hence can easily attacked by strong nucleophilic such as hydroxide, alkoxide, phenoxides and ammonia amines, etc. Regioselectivity orientation of a cleavage of epoxides. Unsymmetrical epoxides can undergo ring opening in two different directions and hence can give different